then you can go over to our GitHub. I'll paste the link in the general chat, that way you don't have to search it all by yourself. Let's see, one of these has to be right. Yeah, there we go. This one's the right one. This one should have the repository. There we go. So you can go to this link in our GitHub. Just pasting that in general. And that should give you the actual repository we're going to be kind of basing off. So this repository will already have the data set. Actually, my lighting is a bit off. There we go. There we go. Should be able to see my face well illuminated now. What was I saying? Yeah, so this notebook will already have like some of the data and such. So if you clone this, or if you haven't used GitHub before, you can just download it as a zip and then unzip it. If you use this, we should be good. The one thing I will say is that if you're gonna like to just download it as a zip, make sure you're on the tutorial branch, because I haven't merged this with the master yet. But if you are to clone this or download it, because again, if you don't know how to use GitHub or Git in general, don't worry about it. You can just click on this code, the big green button. There'll be an option for me SSH. So you can either download it like with this code, right? If you open your terminal, your git clone, or you can download it as a zip. I don't know if it shows the dialog, but then it'll open up a dialog in your operating system to download it to a location. You click save and then you unzip it. Not gonna go over too much about that because hopefully everybody knows how to do those basic computer skills. Otherwise, ooh, I just realized my terminal doesn't show. Wait, does it? I just shared my screen, didn't I? Oh yeah, it won't be showing. Here, I'll show my screen then. Let's see. Change windows. There we go. There we go. So here's my terminal. So if once you do have downloaded, actually I'll go a little bit lazy and just try to find the location where it actually is. So I think it's in Mount. Right now I'm using Windows, but the actual terminal I'm using Linux. So let's see. I should have probably went. Actually, you know what? I'm gonna be lazy here. I'm just gonna kill this one because I know this one's in the correct directory. I'm gonna kill this. So once you're in the actual in a terminal, ideally, if you don't know how to open one, now would probably be a good time to ask. But you know, once you open a terminal and go to that location, right? And then yeah, you should see a couple folders like a data, notebooks, and static. And actually, real quick, I will show you how to open it if you're on Windows, and it should be similar-ish on like Linux and such. Let's see, share. I'm just gonna change. Huh? Yeah, I'm just gonna start showing my screen just for a little bit for now, just so it'll be a little bit easier. It's just I don't want like my notifications and such stuff to start showing. That's why. But let's say you open, you know, your file explorer right here, and then we can go into. Should probably had this bookmarked at least. That probably would have made things better. Wow, none of these are. Where? Whooping. I actually don't know. I don't even know what that one is. I'll be honest with you. So I have so many random stuff that sometimes I'll just see it and I have like no clue what the actual thing is or when. But yeah, you go here. This is my GitHub folder. This thing's in Cancer. So once you're here, if you're on Windows, I believe if you do Shift and then you right click, it'll come up with a couple of extra options here. For example, I get like open a Git GUI, Git Bash, open with code, open Linux shell here because I have the Windows substance for Linux. But if you don't have any of that stuff enabled, you will at least have something called Open PowerShell window here, Open Command Prompt. But I think it should already be defaulted to PowerShell. And once you have it here, I'm assuming that you at least at the very minimum have Python installed. Otherwise, yikes. Otherwise, you can open this notebook. If you do download the notebook and you don't have it, you can upload it to like an online version of this, like an online notebook, like Google Collab. But we're not going to be going over that. Hopefully, you at least have that set up. I think I have Python installed on my actual Windows version. Let's see. Yeah, I do have Python installed. Great. So if you do have Python in this level, right? I do an ls. I get, you know, all my normal files like data and such. Files, I mean folders. One of the main programs you'll actually need to install is Jupyter Notebook. So it should be a pip install Jupyter, if I can type that correctly. And actually, just to be safe, I'm gonna run as the module of Python. So if you run this, upgrade pip. Let's see what the error is. Actually, real quick, Will, do you know if Jupyter is the right package name? All right, you know what? We're gonna do some live advanced stuff right here. We're just gonna Google Jupyter install Python. Yeah, I think that's what it is. Jupyter Lab. Jupyter Lab. Let's try that again. Let's do this. Really? Okay. Let's do notebook then. Why does it keep giving me this? Oh, wait, I think I might know why. Oh, it's permission denied. So I think it's because I'm not running with sudo. So I think that's an error right here, but if you use one of these commands like Jupyter Lab, that one should install it for you. That's just a quirk with the Windows permissions and such. But otherwise, assuming you do have it installed, and actually I'll switch now into the terminal just to make it a little bit bigger. Hopefully it makes it bigger. There you go. Once you're here, what you're actually just going to do is Jupyter, and then notebook. Notebook, not notebook, so that's a file, a folder. I want to run the actual command of the notebook. And I run that, no, because I don't want to autocorrect it. This will actually start the notebook server. And I have to give it an extra command just because of, this is technically in root user. But you hopefully aren't running this as root user, so when you run it, it should actually work just fine. And even more problems. Great. No such file in directory. Wait, what command did I run earlier then? And why did that work? Alright, another advanced tip here. I'm just gonna go, oh, there we go. Mistyped allow. That's why. And no, it's still no. Okay, I'm just gonna go up until I find the command I ran. Jupyter notebook allow root. I guess that command works. Oh, I guess it was the ordering of the argument flag. Once this opens, you'll get a link that you'll actually copy paste into. Oh, there we go. You'll get a link like this, and you can just copy paste that link into your browser as such. Boom, and that'll open up this page. So once you have that, oh yeah, I was just about to switch there. Thank you for that. Oh wait, no, I think this is the right page. All right, cool. And I just realized in the recording it won't show the terminal and such, but you know, it is what it is. It's better than nothing, I guess. It's too late to start over because we're already 15 minutes in somehow. All right, let's continue. There's a couple other stuff like web app and static. Don't worry about that. That just has to do with this whole thing was originally used for something else. We originally made this for the AIMS symposium that they had. That's what we originally made. We made a model to detect skin cancer based on some on photos. And that's why we had a couple extra stuff. We even made a website of it, which we will touch at the end. But for now, if you're just using this notebook, and again, make sure you're in the tutorial branch, because once you click on notebooks, you won't find the specific notebook we're using. But once you click on notebooks, In this directory, there's going to be a bunch of notebooks. You'll want to go to the last one, which is called just tutorial, and open that one. And that's why it's important you're in the tutorial branch, because otherwise that notebook won't be there because I didn't merge it to master yet. I am going to merge it to master after this, once I push all the actual new code that we will have written. Cool, so now you have this. So I guess a quick crash course on what Jupyter Notebook is and how it works. It's essentially a kind of like a more interactive Python interpreter, if you want, right? You have these what are called cells, and these are like snippets of code, and you can run them each cell individually, and then you can run them out of order, right? So if you modify something earlier, you can run that one thing instead of running like the whole program all over again. And it's really nice for data science, especially because you can have a couple stuff like you can print some of the images into the output and you don't get an extra window. So it can be really nice for any scientific stuff. Also, I just realized now, Peter, are you in the public or something? Peter, you're muted. There you go. Are you in public? Oh, all right, fair enough. Well, we'll just continue then. All right. Yeah, I was like, why are you dressed up like you're gonna raid a capital? There you go. Little joke for the day. All right, let's continue though before I say other stuff. So the first cell, you don't need to run this if you already have the stuff installed, but if you're just like new to this, you probably won't have some of these libraries and packages installed. So what this first one will do, and this is where you can click run to actually run the cell once you have it selected. So what this will do is this will pip install a couple packages that we're going to be using. One of them is NumPy, which is really good for any numerical arrays. It's Python is an interpreted language, but a lot of these libraries are written in a lower level language, which essentially means that they run pretty fast despite being in Python. Matplotlib is to render nice charts and plots. Pandas, I think I just realized, I actually don't use Pandas for this notebook, so it's actually unnecessary. I can remove that one. And remind me in like 10 minutes into this notebook where it turns out we do use it and I immediately regret deleting it. But otherwise, we should be good without needing that one. And then the last two that we should be, actually, FastAI was also one that I was using originally, but not anymore. We're going to use TensorFlow, and that's what we're actually going to be using to create the machine learning model. And we're going to be using Keras as a higher level API because using TensorFlow directly, it's pretty complicated and we don't really need it. So once you run these pieces of code, and right now, all these, the dev know what this is doing is there's going to be a bunch of output of download and just not clutter the whole notebook. I just decided to not really print that. But if there's any errors in the installation, it will print that out. So if there's any errors, it'll print it. Otherwise, you shouldn't have to worry too much about it. And also, I just realized it's still running. I don't know why it's still running. I guess it's downloading some stuff that I didn't run before. Oh well, it is what it is. The next step you'll do is you'll import all the actual packages and specifically any modules that we actually need for the notebook. In this case, I have OS because we're going to be doing a couple stuff with like some folders and subfolders. So we need the OS module for that. We're importing our NumPy, Matplotlib, and then as you can see for all our TensorFlow, we're importing everything from Keras. So here we're importing the sequential model. And then here we're also going to be importing some layers and losses. And then finally, we're going to be importing an image data generator, which is going to make working with all those images a little bit nicer. It's going to make our lives way easier than writing our custom scripts to import every image and so on. There we go. So that one finally finished running. As you can see, when it finishes running, it's no longer an asterisk. It's going to be a number depending on the order that you ran things. So when this one finishes running, it's going to be 2. And if I were to rerun this one again, after that one were to finish, it become a 3. And that's there so you can essentially know what ran in what order. Because if you're running things that you ran initially and then other stuff and it's all over the place, it'll make things a little bit easier to track and you know what's actually going on. So any of that hopefully made sense. Any questions so far? All right, I'm gonna take that deafening silence as I understand everything you've said. Or no, but that code's already written, so who cares? We'll move on. All right, thank you for the enthusiasm. We'll move on then. So the first thing in this block we're going to be doing is I'm going to be going into the data folder. So if you remember how the directory of this was, if I go back here and I go into this root, right, we're in notebooks and we're in this tutorials, right? So what we need to go is go up one level and then go into the data folder, right? And if you can see, right, if we want to go up a level, you can click these two dots. And that's how essentially the syntax works here, right? We're going to be going up a level into the parent directory and then going into the data folder. And that's going to be our root folder for all the data. And then over here, we're going to be telling it what the training directory is and the test directory. As you can see, we have a test and training. And then specifically each class, the benign and malignant for each training and testing. This is already pre-done, so it makes a lot of this other stuff easier. Sometimes you won't have any of this done and you'll have to split your training and testing data set by yourself. You'll have to do it manually. Well, again, there are some modules out there, scikit-learn or scikit-learn, or it has like a function kind of for that where you can split your training and testing data set automatically. So it does make some stuff nicer. But the advantage here, having separate folders, is that everything's kind of already pre-labeled based on what folder it's in, which is very important when you're doing supervised learning, because again, you want to map an X to Y, so that Y, you want to know what the actual answer should be. You need to know what the label is, right? Because it doesn't serve us much if we have all these images, but we don't know which one's actually benign and which one's actually malignant. And now that I'm saying benign and malignant, benign means that it's not what? I think it should just mean that it's not skin cancer, or at least it's not something that will kill you immediately. And malignant means that it's something bad. Your body made an oopsie and you should probably go to the doctor. And it's Biology 101 by Gino, yours truly. Anyways, so we run that one and no errors. That's great, right? If you do get an error, it might be in terms of directories and such. It's probably going to be something related to that. Hopefully you shouldn't, because if you just downloaded this and didn't mess with any of the locations of the files and such, it should work just fine. Now this one, again, this was kind of pre-written because it's not as important for the rest of the notebook, but I'll still go over it just to kind of know what's going on. One of the things here that's going on is that we're going to be doing this for the training and testing, because we're going to have separate generators for each one. The rescaling here, what it's doing is that every channel of a pixel has a value ranging from 0 to 255. Now, where we're going to be using in the actual model, we don't want to use numbers that range from 0 to 255. That's a very big range. So we're going to squish that into something from 0 to 1. And you'll see throughout a lot of other machine learning notebooks and some other machine learning, you'll see that a lot of times we'll want to squish values from a range of 0 to 1. And it's very useful. There's a lot of nice things you can do once you have that assumption. But that assumption plays a little bit more when you go into stuff like activation layers and such, which we will briefly cover in the notebook. Hopefully I'm not talking too fast. The next thing here, and this is basically the same thing for both of these. The extra argument here is the shuffle for the training one. Essentially what is this doing, right? Your directory to know which actual directory it wants to import the images from. The shuffle, it just means that when it's going to be importing all this training data set, if it wants to, when it's creating that generator of images, think of it mostly, generator sounds complicated. Think of it as just a big array, right? When it has that in an array, do you want it in order or do you want it shuffled? In this case, we're just going to choose shuffled. Another thing is target size, right? When it imports all these images, it's all going to normalize into one size. And this is important because your data set might have different sized images, right? You might have a 10 by 10 pixel, well, actually probably not 10 by 10. You might have like a 200 by 200 pixel image, right? And then the next picture might be a 4K high resolution image, right? And you want to normalize them because when you're actually going to pass it through the model is going to expect one size only. In this case, we're going to choose this number, 224 by 224. Why? If you go and look into the actual images, go into this one, click one of these images. Also, if you're a bit squeamish, you've been warned. Probably should have gave a little warning a little bit earlier, but I mean, you saw the title of this, right? Skin cancer, so it's kind of on you if you still decided to show up. But as you can see here, the image is 224 by 224, and so so are all of the other images. You can verify, but don't waste your time. Just take my word for it. And that's why we're choosing that number. So, and this is actually where I open something on my other screen because I'm going to cheat here. That's that. Now we sort of imported our data. And now we want to see, okay, what size are going to be our actual, each image, what size is it, right? Is it actually the 224 by 224? Well, we'll see. So, as you can see, one of the variables here, it's called train data gen. We can run that. It gives us what the object is, not very useful, but we can call a specific attribute of it. And now we see this. Okay, now we know what the image shape is. What is it? Again, 224 by 224, but now it's by 3. And here's where I turn it onto you guys. Does anybody here know why that 3 is there? And you can just, yes, it's because it's 3 channels, right? In the images, as you saw in the original images, they were in color. Computers, when they represent images, right, most, like 99 of the image formats I've seen, they use 3 channels to represent colors, typically being something along the lines of red, green, and blue. At least that's how displays do, actually. Image formats store things differently, but that's a whole nother issue. But when you actually display it, you're right, you can have something in a red, green, and blue channel. And that's why we have 3 here, right? In some other data sets for some other stuff where color might not matter, you might just have it in grayscale, so you might only have 1 channel, right? So that 3 might become a 1. In this case, again, I'm not a biologically or medical expert, but I would probably guess, right, if I had a hypothesis, I would probably say if you're looking at skin cancer, the color might play into things, right? You know, if you look at my skin here, it's pretty pale-ish, right? If you look at this, okay, you know, not a big deal, right? But if you saw something like that was green, and it wasn't a tattoo or anything like that, if you saw something green, you probably wouldn't think that's normal. You'd probably tell me to go to the doctor, right? And that's why, right? But if you're looking at this at grayscale, it might be, okay, maybe it's some sort of like birthmark or something, right? You wouldn't quite know. So that's why color, I would argue that it's important. But again, somebody here is better medicine. They can tell me that I'm wrong or just approve that I'm right and maybe add something onto that. Cool. All right. I'm right like usual. That's my confirmation. There we go. All right. So now we are going to showcase a couple of the images. So here, I'm actually going to, probably should have included this one in the actual notebook. So I'll just copy paste it in. You don't have to worry too much about this. This is mostly like Matplot stuff. But essentially what we're going to be doing here is that we're going to be inputting an array of images. It's gonna, like 5 images it should be. I think this is already assuming it's only gonna be 5 images. And it's actually gonna be printing those into the notebook so we can see, you know, what kind of images are we looking at. Which is a bit easier and more intuitive and faster than just do what I did, which is go image by image into your file explorer and trying to see all the images, right? So what we're going to be doing here is a little bit of Python magic, which again, not the biggest, most important part of the notebook, but I'll still go over it. So what I'm doing here is I'm going to call next on this generator. And what the generator is actually going to be doing is it's going to give us essentially, actually it's a quite a bit more advanced Python stuff, but what, I'm going to lie a little bit here, but I'm going to simplify it. Think of this generator and this next function as essentially returning us like an array of images. That's probably the best way, and it's enough you need to know for this. If you know the actual reason, don't worry, then I mean you don't need to know explanation, but otherwise don't worry about it too much, what exactly it's doing. Just think of it as giving you an array of images. And now we're going to call this function, right? We're going to give this, actually I'm not going to type that, I'm just going to copy paste that. We're going to give this, and again here we're going to do a little bit, you could kind of say advanced Python, but we're essentially going to pass it the first 5 images of this array. Now if I run both, right, first I need to run this one to actually define the method, and then I run this, and once it runs, and also why is it taking longer than usual? My computer, probably should have killed some resources beforehand. Oh well, it is what it is. As you can see here, we see a couple of images. Now off the top of my head, I can't tell you which ones is benign, which is benign, which one is malignant, But if you did want to know, it would be in this variable right here. The reason why we do this, right, is another thing you might have noticed is that when we're doing this equal sign, right, to find a variable, we're actually defining two variables here, and the last one is an underscore. What are we doing? Because when you actually have this generator, it's actually going to essentially return you an array, but each element is going to be a tuple. And so what we're doing here is we're doing tuple unpacking, right? The tuple is a size of 2, and so we're going to essentially give one element of the tuple into one specific variable, and instead of doing some more like complicated stuff where you give it to a general and then you do indexing. This is a little bit easier. And then the underscore is more of a convention that we use because we don't really care about the labels here. So we're just gonna give it to an underscore to essentially be like, well, we need it for the actual code to work to not return an error, but we don't actually care too much of what the value is. All right, and then the next part will be actually creating the model with Keras. And before I go here, any questions so far? Because I'm assuming some people might have been lost here with the tuple unpacking and array indexing. Hopefully not. Yeah, no problem. So Keras is a high-level API for using some machine learning libraries. So I believe you can use Keras like with PyTorch, for example, which is another machine learning model. Here we're just going to be using with TensorFlow. And now whether you use TensorFlow or PyTorch, which one is better, too much to get into, but just so you know, PyTorch is just fine. I think in some cases it is better than TensorFlow depending on what you're working on. But for this one, I personally know TensorFlow, and I've worked more with TensorFlow using Keras, so that's the one I'm going to be showing here. But you could re-implement this all into PyTorch, and you probably get the same results, or better. Who knows? That's part of the scientific method, right? You test different things. But yeah, when you look at a neural network model, right? If you've seen all those images here, we'll look at one right now. Neural network. We go into images. Right, you get something like this, right? Complicated. There's a lot of fancy math. Look at this one. So many connections, right? There's a lot of matrix multiplication, gradient descent. There's a lot of advanced mathematical stuff. And if you use something really low level, like the actual TensorFlow library, you can really get nitty gritty with that sort of stuff. But if we're trying to get something like just kind of fast, done way more faster, we use that API, which abstracts all of that, takes care of all those complicated stuff for us. So instead of being super specific on a lot of these like very nitty gritty things, we can kind of give it more high level orders and being like, I want this many layers, I want this layer to be like this layer to be like this, I want this layer to have this size, and it'll take care of all that for us. That's essentially what Keras does. All good? No problem. All right. Yep. If you're talking about, hopefully it's the answer you're looking for. If you're talking about here, when I rescaled, yeah. Is that what you're asking about? Yeah. So yeah, so the reason we divided by 255 is because if you remember earlier, as I said, all pixel values range from a number of 0 to 255, and we want to squish that to a value of 0 to 1, right? So if you had a value of 0, for example, right, you divide that value by this number, or I guess multiply it in this case technically, but this is essentially doing a division by 255, right? You end up with 0. So at the lower end, you'd still get 0. But if you want to get something at the highest, most possible end being the 1, 255, and you want to map that to a 1, then you're going to divide that 1 by 255, right? And then everything in between will get squished to its proper range within that number. Yep. Yes. For something like output, that would come even more handy. But in this case, it's also just for the weights, right? you don't need as big of weights. All your weights for each, again, hopefully it's still there. There you go. So if I open this one, it's a little bit steeper model, right? If you see all these lines, each one is an individual weight, right? When it propagates the value. By having values that just range from 0 to 1, they're being pretty small values. The values of the weights themselves also don't have to be too big. And that helps with the actual learning rate. No problem. But yeah, but if you have something at the label end, right, if you actually label data for zeros and ones, it's also really handy, especially once you start getting into the activation functions, which we will briefly touch on. So yeah, that's actually a really good question. Thank you for asking. All right. So now here for the actual Keras part, right? We're gonna start creating our model. So we're gonna call this just model because I'm very original when it comes to names. And this is where we're gonna be calling our sequential class. If you remember that we imported earlier. And this sequential class, it can take an array as an argument. But an array of what? An array of layers. Because if you look at this image again, right, you can essentially think this neural network as essentially an array of layers. All right, this one being like 4, then 5, then 7, and then 3. So that's essentially what we're going to be doing here as well. We're going to be just defining each element being some sort of layer. And we're working with images. We're going to be touching something which calls convolutional layers, all right? And what this essentially does is it's going to abstract the image in a little bit more. I mean, obviously when you make it deep, it'll abstract all the features of an image. But what the convolution actually does is that it's going to make it essentially a bit more independent of its positioning, right? And this is maybe something I can touch on in the future. I do have a notebook. Oh, yeah, no problem. Wait, what's going on? Did I... Hello? Am I here? Can you guys hear me? Oh, my internet. There we go. I don't know what happened. I literally just disconnected, reconnected, and that apparently my bars went back to green, so maybe that did something. We'll never know. But it is working now. All right, so I'll just hopefully I didn't say too much before I disconnected. But as I was saying, we have these layers, and actually I was talking about the convolution, right? So I do have a notebook we can go on in the future, maybe in another meeting, to kind of showcase exactly what I'm talking about here. But essentially, if you give the same image and maybe you translate it or you rotate it and such stuff like that, it'll be more resistant to that. The model won't recognize some completely different image. It'll kind of see in its head that, oh, well, it's not exactly what it's doing, right? If you look at the mathematics of it, but at a higher level, you can think of it it's still recognizing it's just different, right? If I show you a picture of my hand like this, right, and then I move it slightly, it's still essentially the same thing, right? The only difference is that it's just shifted slightly. And that's essentially what the convolution does here. It kind of will account a bit for that, right? So if I have my hand here versus here, the model will essentially recognize them as virtually the same thing. As opposed to one that doesn't have any convolution, it'll see those two images are basically completely different. Hopefully I'm still in the green and not disconnecting or anything for anybody. But yeah, if I do that again, just point it out, because I was able to hear you guys, at least when you said that I was dead or something. I think that was Dylan who said that. But if that happens again, just tell me. So one of the first layers we're going to be calling here is that convolution layers I was calling. So one of the first parameters you have to pass to it, and this will be the same thing for a lot of other layers, is you have to give it how many neurons for that layer you actually want to have. So in this case, I may call something like 16. I want 16 neurons for this one. And then for the next one, I will have to give it some sort of value, being the actual value for the convolution kernel. And again, this goes a bit more into the mathematics, but I'll quickly show what the kernel is. An image. There we go. This part, hopefully you can see it well. There we go. Oh, that's way too big. There we go. This part here is the kernel. It essentially looks at a subsection of the image and does some matrix multiplication. And that's what we're going to be defining right there. It is the size of that actual kernel. Now, if your kernel is going to be square size, you can just give it one number, just being like, for example, 3. But if it's not going to be a square, it's going to be a rectangular shape, right? You can give it a tuple of those two numbers, right? In this case, 3 and 3. So this 3 and 3 in a parentheses making a tuple, or just the 3 itself, they're the equivalent. They're the same thing. And next thing we're going to be defining here, which you don't have to, but obviously it's recommended that you do, is you give it an activation function. In this case, we're going to be calling a relu, which I'll open an image of that as well. Activation functions. If you look at a couple of these, right? If you look at the relu, what this does, it essentially, any value greater than 0, it maps it 1-to-1 ratio, but any value that's negative, it just gets mapped to a 0. And then finally, you have to declare what the input shape is. So for this first layer is actually one of our hidden layers. You don't actually define the input layers as its own layer. When you're working with Keras, you would actually just pass that as an argument for the first layer of your model. You essentially give what's going to be the input shape, and then it'll implicitly create that layer for the model. And as you remember earlier, what was the size of it? It was 224 by 224 by 3. And that's what we're going to type in here. And now when you do convolution, you also usually do something else with the convolution, which is just called pooling. In this case, usually it's just going to be max pooling. And again, I'm going to be calling a layer called max pooling 2D. And here you see there's convolution 2D, max pooling 2D. It's because our data is 2-dimensional, right? The images are 2-dimensional. There is a 1-dimensional, there's 3-dimensional, and I think there's even 4-dimensional. But we don't really touch on those, so we're not going to be using them for this one. But though I'm just saying that to show you that it does exist. And then we're going to be creating a pool size. And then this is the same thing as that kernel. We can either give it one number, or we can give it a tuple for the size. And what's max pooling? I'll open one more here. Max pooling. That essentially will take again a subsection of that image, and then it'll take the maximum value and upload that to like another image, right? And that's what that one does right there. And those two things together combined is kind of what give a convolutional layer a bit more data resilience or transformation resilience, right? So even if you change your data, the images slightly, it'll still essentially recognize them as the same thing. And now the next thing we have to do is call a flattened layer. And this is important where we're going to be, because again, now so far our data through this, as you can see, as you can think of it as a pipeline, it's 2-dimensional, right? You got your X and Y dimensions. We're going to be flattening this into like one big array instead. And this is, you kind of need this where you're going to be doing something like a dense layer, right? Which is the next layer we're actually going to be calling. So we're going to be calling layers.dense, and I'm going to give it just like 10 neurons, for example. And again, I want to call an activation. I'll call an activation of relu. And now you may ask yourself, okay, now what is the dense layer? And that's pretty simple. That's those layers that you saw here, right? And why it's called dense is because every single neuron is connected to every single neuron of the next layer. So they're all densely connected. And then finally, we're going to call a layer of another dense of just one size. And now we're going to also be given an activation, which I'll touch on quite soon enough. Now, why am I calling it of 1? Well, this is going to be our final layer. It's going to be an output. In the end, we just want to have a value of 0 or 1, indicating, is it malignant or is it benign? So our output layer has to match the size of our output labels, and X is just one. Now, if you're classifying many different things, then you might use something like a categorical representation. You might use one hot encoding, in which case you will have X number of neurons for the output layer depending on how many things you're categorizing. If you're only categorizing two things between two different categories, you can actually use one output instead. But otherwise, you can use something called one hot encoding. And now we're going to be using a sigmoid activation function. And now you may ask yourself why. Now sigmoid here, as you can see in this equation, it ranges from 0 all the way to 1. But no matter how small your values get, right, up to negative and down to negative infinity or positive infinity, they're always going to stay within the confines of 0 to 1. And this is important because in the end, we just want a number that's 0 or 1. We don't really care about 2 because that doesn't mean anything for us. And then you might ask yourself, well, why don't we have sigmoid everywhere else? Because why not? And that kind of gets more into the mathematics of how the models work. But long story short, if you use sigmoid everywhere within your model and you have a very deep model, which essentially means there's a lot of layers, the learning is just gonna be slower. And we don't want that. We want to learn relatively fast, at least for this workshop. So we want to keep it as simple as possible. And now here I've just defined the model. I've essentially created the model, but I still can't use it. Now I have to compile that model. So I'm going to call model.compile. And here I'm going to give it a couple of arguments. So the first one is an optimizer, which, again, it gets more into the mathematics, but that essentially is what algorithm or method is it going to use to actually update itself and learn, right? How is it going to improve? What learning method is it going to use? So we have to define that, and we're going to use Atom, which is pretty standard for the most part. But again, if you don't know what that one is, you don't have to worry about it too much. We can always talk about it after this, or maybe on future meetings and such. So don't worry too much about it. But essentially, it's a pretty standard. You can also, another one I've seen quite often, but not as much, is SGD, which is Stochastic Gradient Descent. Which again, it's kind of going to the mathematics of it. So don't worry about it too much. And in here, I'm going to be calling my losses. So if anybody has taken, actually, who here has taken a statistics class, like 151, or even statistics back in high school? Dylan raised their hands. Brendan raised his hands. All right, so a couple of you have taken this. So you can essentially, I'm going to give you an example of one such loss function you can use, which is called your mean square error. In this case, we're not using it because it's not the right tool for the job. But essentially, it's going to tell us how far off were we from the answer that we wanted, right? Because if it's going to learn, right, it needs to know what the mistake was and by how much, so it can update itself, right? And this is the same thing as if you're doing, well, now because of the pandemic, if you do an E-class quiz, right, and then you look at, well, assuming your professor was nice enough to then include, what you did wrong afterwards, you'll see, okay, I got 0 points here, I got 1 point here, I got partial marks because I did this, and then even if you don't have an explanation as to why, you can kind of piece together, okay, this is the mistake I made, and then here's how I'm going to improve it in the future and such. And that's essentially what this loss function is. But this one is specifically one that we use if we have binary category, which essentially means we have two categories and we want to know which one of it is, and where you have to use this specific loss function. Although you can use categorical cross entropy and it'll work just fine for this as well. But if you're using a binary categories, then you might as well use binary cross entropy. And then finally, because we're not doing like a regression, we're doing a categorization task, we might want to know some extra metrics of this, such as is accuracy. And so I run that, and boom, now it's actually compiled that model into something that now we can use. But again, it still hasn't trained, it's still not good at all. If we were to try to run this, it would pretty much just be guessing randomly. It might even do worse than like 50%. And now here we can print out a small summary of our model, which will give us some information based on how many parameters we have so far in the layers. As you can see towards the end here, we have like a million, almost 2 million trainable parameters, right? So it's a lot of computation of the computer. So it might take a while, actually. In the notebook I have, which has, it's a little bit deeper, it's got more layers and such. I have a size of 20, yeah, a little bit over 22 million parameters. So it definitely takes even longer. If you want to improve the computation, there's a couple stuff you can do. You can first of all run it on a cloud server, which has a higher, computational power. Another thing you can do, you do have to set it up, is when you're gonna install TensorFlow, you can use it in TensorFlow GPU version, and you can go to this link into the TensorFlow documentation to see how you can set it up on your computer, because it'll change depending if you have like Linux or Windows. I assume there might be a Mac tutorial, but I mean, if you're running complicated models on your Mac, I'm sorry, but you're probably doing it wrong. No need to bash on all the Mac users, but it is what it is. Yep. Yep. Mm-hmm. So what you're describing there, it would be more like a feature, right? If we think of features of our image, right, we might want to. For this one, there's really only like one feature we would really be looking at a high level, which is the actual area that might be benign or benign. But if you were trying to run a machine learning model on me, and if I was posing like this, you may have different features such as my hand, my face, my torso, maybe my headphones, maybe the door in the background, right? When you're running these models, and you're running something called a deep neural network, it'll abstract that all for you. But the parameters here, what they actually mean, is essentially the neurons, right? How many neurons do you actually have in this layer that you have to update? That's essentially what it means, right? So again, if you look back here, oh, wrong one. Close that one actually, right? This how many neuron, actually not even neurons, but like how many weights do you have to update? You have to update this one, this one, this one, this one, right? You have a lot just for the first layer. And then you would also have something like the bias weights, which you would have on top of every other hidden layer, every other neuron for each layer. So that creates a lot of parameters that you would actually have to train, a lot of neurons, a lot of weights that you actually have to update when you're running this model and updating it based on what it learns. So that's the one we see here, right? The almost, but not quite 2 million, right? And then you can do the math by yourself if you're so inclined. But as you can see for this first layer, how many parameters do we actually get out of this? Well, we get 448. And that's another advantage of the convolution part, is that it actually doesn't create that many. Again, that's if you go more into the mathematics of it, which I can go over in another meeting. People really want to learn about it. But that's the number of. Yeah, you can kind of see the us connections between each neuron. All right. And then this next one, oh, yeah. It's a good question. I think it's going to show us. Oh, I don't think it shows there. I think it says somewhere earlier in this notebook. So here it doesn't distinguish it quite, but you would have in total this many number of images for the two classes across the two classes. I don't think it would say right here, but we can kind of be cheeky about it, and let's see if I go here. I like you could count, right, how many images do you have in this folder, right? If you go on Windows, select all. Yeah, there we go. So 360 for benign. Thank you, Dylan. And for malignant, on the testing data set at least, we'd have 300. So it's almost, what was the other one? 360 or 306? 360. So it's almost 50-50, but not quite. But I guess this is something else that you might want to consider with your data, right? You might want to make sure that everything is well represented, that you don't have any like clear biases or lack of data in your model, because in your original data set, because your model learns that and it will sometimes amplify that. And then that's something you may have heard over in sometimes in the news. For example, when you hear of racist models, right? You may think of yourself, well, how can a computer be racist? Which is, well, the computer itself is not racist. All it's doing is just math, right? Right? The math itself is not racist. But the data set that the researchers or company might be using might have flaws in it, and they might not realize. And when they train that model on those flaws, it might amplify those flaws, and that's how you might end up with a racist model or just discriminatory model, right? And again, this might be for different reasons. That's honestly a whole nother topic, which I don't think we talk about it all that much. But if it's something you guys want to talk about in the future, it's 100% down for it. But that does fall. Yep. Yeah, yeah. Thank you. Yeah. Yeah, that actually, yeah, thank you very much for pointing that out. I didn't quite think to mention that. But yeah, that would also play into it, right? And if you're running this for something way higher level, again, you would want to have an even bigger data set, and you'd want to make sure there's no problems in the actual data set and such. But for a workshop that I'm doing for free on a Friday night, this is good enough. We'll just say. All right, I'll open the other notebook with all the answers because I don't like typing everything by hand. And so now here we're going to be, actually I'm not going to type the code because writing the code itself is not that important in this portion. But what essentially we're going to be doing here is we're going to be getting the total training size and the total testing size for each of these, right? What it's going to be doing, it's going to take a list of all the images in these directories, going to take the length of it, and it's going to add them together. So that's what we end up when we run this part of the notebook. Now we have our total training data size. We can actually start training our model. So far we've compiled it, we've even looked at more details of it, but we actually haven't trained it. So now that I'm going to start training it, I'm going to call model.fit. And it's going to essentially fit our y data into our x data, or x data into our y data. Right? It's essentially going to optimize the actual model, because if we were to run this model, which we can, right, it's not going to be very accurate. It's going to essentially be doing no better than just guessing randomly. So the first thing we have to do is pass the training data. In this case, we pass the training data generator. If in some other data sets, depending on how you split it, you might have your x and y data explicitly separate, in which case you'd pass both as separate arguments. In this one, we have a generator, so it's kind of all included in one nice package, so we don't have to. Let's see. There we go. I can type. The next thing we might call is something a batch size, which I will go over quick. Actually, we don't have to specify this either, right? The rest of these are optional parameters. You don't have to specify them. The only one you really need is the actual data, obviously because you need the data, but the rest is just something called hyperparameters, which affect how this will learn. So now epochs will define something like, actually I might even make it shorter just for a quick demonstration. We'll make something like 2. And then, this is one I'm going to copy the code again because not as important to type it out. How many steps we want to take per epoch, being the number of our size divided by the batch size, which in this case is 128. The reason we have a double division sign is a specific Python language feature, which when you divide those two numbers, it'll return you a float. Will most likely return you a float, right? If it's not some like perfect number, right? If it's 1/3, it's definitely going to return you a float, which is almost like a decimal, right? It will return you like 0.33333. And in this case, we want it specifically an integer, so we want to have like already kind of like pre-rounded. So we give a double division sign, which will specifically tell when you do this division, give me a whole number, not a partial number, or I guess a decimal number. And then that's how many steps we want to take for epoch, and then validation steps we want to essentially be the same size that we would for our count as our epoch. But this is, again, you don't really need to specify. This is an optional thing you can do. And then here, validation data being our test data generator. This is the actual data set we're going to be validating our model. And why do we need to validate our model? Because we can get our model to be really good on the data that we trained it. We can if you train this long enough, it could get 100% accuracy based on the training data that we have. But then we run into another problem, which is called overfitting, which is our model's really good with our own data set that it's trained on constantly, but once we try to show it new data, it doesn't know what to do. And this is essentially the equivalent of maybe your professor or T graciously giving you a example test that you can take before your final, and then you take that test, you retake it over and over again, and you've done it so many times that you've essentially memorized all the answers by heart, right? But then you go to take the actual exam, and then all these questions that are different questions, you don't know the answers of it, because all you remember was heart by heart. You remember all the answers for the test exam. And now you'd be screwed, and you'll probably get a 0. You're going to drop the class. And next thing you know, you're dropping out of school. And you don't want that, right? So here we do validation, which essentially it's going to then take something else that it hasn't seen before, that hasn't trained on before. It's going to see it, and then we're going to see, okay, is it actually learning? Is it actually generalizing that knowledge, right? Is it learning? And then we can see if it is overfitting, right? If we can get like 99.9% accuracy on our training set, but then when we actually go to test it, we only get like 40% accuracy. And then we see, okay, we've overfitted our model. We got to make some changes. Probably should have started running this before I went to explanation, because this is the part that's going to take a while, as you're going to see here. But actually, while it's going, I'm going to explain a couple other parameters. Our batch size. What is a batch size? And this kind of goes into like what gradient descent is, but essentially, when it looks at all these images, I'm actually going to drink a little bit of water. Been talking for quite a while. But when it sees all these images, you know, as you remember, it has to update itself, right? All these parameters, it has to update them to kind of readjust itself, right? And then try to get more accurate. And the batch size is essentially just indicating how many points of data does it want to see before it actually updates itself and it improves, right? And we set it at 128. Now, what is epochs? An epoch is essentially like a whole run through of the data, right? So if you look at the data once, like if you went through it, like all the data, and you went through it once, that's one epoch. And we might want to run this multiple times, right? So it can learn a little bit more. So you might give it a different value. The default of this is 1, so if you didn't specify this, it would just run it one time with the data, and that's it. Steps per epoch. You might think, well, is this kind of similar to the batch size? Not quite. This is an extra parameter you can give it, which is essentially telling it to define it what an actual epoch is. If you don't define it, it'll go to the default value of, well, you know, just how much data I have. I'm just going to throw all of it. That's it. But you might not want to exactly do that. You might not want to always go through the data once for some reason. You might want to go a little bit less. In this case, we define it to be the exact value. The mathematics here works out. And we just give that extra parameter in this case, even though the default value would do that, just because when it prints here, it knows how many steps it's actually going to be doing, because we're using a generator object, which goes into the specifics. But if you didn't have this piece of code, it would still learn it would essentially learn the same. It's just that when it's running this, instead of showing out of 20, it would show out of unknown. And validation steps, it's kind of like the steps for epoch is how many steps, right, it's going to take when it's running its validation to see how accurate it is. As you can see here, even it's starting to give us a couple of values of the model. And the last one, which probably might have been one that I might want to include it, is we're going to quickly show how accurate our model is. I'm going to paste that in. I probably should have written that, actually. So you see here, we have a model. Actually, I was dumb enough to not include, to define it, right? Because this is, I'll put this value that we see here, but I want to now give this value into a variable being history. Now I have to rerun this model. Now we have to wait a little bit more. But if you look at this history, right, it'll have a history attribute, and this history attribute will essentially be a dictionary. If you were to run this, you'll see that it's going to be a dictionary. Now it probably won't run yet because this has to train, but after that it'll run that. Now here you see it's a dictionary, right? We might want to get then specific attributes or specific values out of the dictionary. So one of them is the accuracy, another one is the validation accuracy, the loss, and the validation loss. And this will essentially show us for each epoch, right? Each period over which we went through the data once. It's one where we'll essentially have one graph where it's going to be showing us what the accuracy was, both with the actual training data set and the testing data set, and then another one for the loss, right? So we can see, how did it improve over time? Did it ever plateau, right? Maybe it plateaued really early, right? In this case, we're only running it 2 times. We're not going to get much scientific analysis out of this, but if you were to run this 100 times, you might notice, well, our model basically learned pretty well after 50 runs, and then afterwards it just never improved. It might be something good to know. And then here we do a little bit of Matplotlib stuff. And this, essentially what we're doing here is we're creating some subplots so we can show this all in one output. And then here we're going to be labeling, but this is actually where we are going to be plotting the actual accuracy values, the validation accuracy, the loss, the validation loss, and we're even going to give a couple of legends just to be nice, and even some titles. Hopefully this runs. But as you can see here, quickly, just to do some quick analysis, you can kind of see in terms of its accuracy, 54%, actually validation, 54% accuracy, 54.8. It's not the most accurate model. As you can see here, it looks like the lines are going very up and down, but just look at the y-axis and you realize it's really just ranging from like 0.55 to like 0.54, 0.3. I don't know why that's going kind of inverse, but you can improve this in many ways, and I'll show you one of those ways, right? Affecting how the structure of our model actually is. And this is something where you can go afterwards and really go into it and see, can I make a better model than Gino? Which the answer is probably yes. If you spend more time than me, you probably will end up making a better model. There's a couple things we can do here. For example, just a little bit of copy and paste here. Good old programming is just copy and pasting. We can give her more convolutional layers, right? And for some of the convolutional layers, we can give it even more neurons, right? So instead of just 16, let's give it 64. Why not? We got the computing power. This dense layer that we have here, let's make it 100, right? And you might run this model now, and then it'll have a certain amount of accuracy. Now, let's say that, for example, we were overfitting this model, right? So we're getting 80% accuracy, but when we actually ran it with our validation data set, we got an accuracy of like 50%. We overfitted. So that's, I guess, a little advanced gamer move we can do right here is we can call it Dropout Layer, which, long story short, it'll help us kind of generalize it, help the model generalize a little bit more. What it's essentially doing here is it's essentially going for all those weights, right? All those connections at a 20% of the time, essentially, it's just going to drop that connection. It's not going to propagate the information across the neural network. And then you might ask yourself, Gino, why would I want to do that? Don't I want to pass along that data? Normally, yes, but if your model is overfitting, this is a way you can kind of help regularize it, right? It's a regularization method you can use. So essentially what it does here, it's not going to over rely on any specific parameters in the whole model. It's going to essentially kind of generalize that over across the whole model. So it ends up being pretty good. And this essentially can be, for example, right, if you're trying to improve yourself in life at a high level, right, you may think of this, right, you may know your strong suits. All right, I'm really good at math, I'm really good at, or let's give programming languages, right, because I assume a lot of people do computing science, right? So let's say I'm really good at Python, I'm really good at JavaScript, but I'm not that good at C or C++. I might want to improve those areas a little bit more. So you're not over relying on one specific technology. That's kind of, in a way, what the model is doing here. It's not going to rely on any specific neuron to do all its classification. It's going to really rely on most of them. And that's how you can kind of think of it. But anyways, I ran this model. Now I have to run these again. I have to recompile it. I can get a new summary of all the new layers and the parameters, and you can see we've essentially doubled our number of parameters. Like we've got 4 million, which is twice as much essentially, right? And now we might want to run our new model and see how well it trains. And we might run on this one as well. And then finally, right, you can see here, right, that dictionary I was talking about, right? Each value is going to essentially just be an array of the numbers, and that's what we're going to be plotting right here. I'm going to delete that. Right? And that's, yep. Yes. Yes, actually, that's something I forgot. Yeah. Something you could do here is actually, and in my notes here, I do have an epochs of 5, for example. So you could up the number of epochs, right? Or you can mess around with the batch size. You can mess around with a lot of hyperparameters, and that's kind of a big aspect of this, right? When you do machine learning, at least supervised machine learning, is a lot of it's going to be, well, first of all, a lot of it's you're going to be cleaning your data, because whatever data you originally have, it's not going to be very good, and you're going to have to clean it. But the second thing you'll spend a lot of time doing is probably just messing with hyperparameters, right? Because whatever hyperparameters you're using might not be the most optimal ones, and you'll just kind of go methodically and try to get better values. And that's actually something we did, me and my teammate of mine, which is actually in this call. Its name tag is on Discord is Y Kisana. Something we worked on in our reinforcement learning class when we worked on a notebook together. And we were trying to recreate some experiments. We had to mess around with hyperparameters to try to get the most optimal run. And the same thing here for supervised learning. You might want to mess around with hyperparameters to get a higher accuracy. And the more you play around with them, you might get something really high. But something that also affects it a lot is the structure of your model. And that's something that we can see in the final product. If I go into, actually that's something I should probably, actually if you go into our GitHub, right, this link right here, it'll show you into this little game that we made out of the whole thing, which I'll cover quite soon enough. But that one's using a different structure, and it still uses the same data, but the hyperparameters are also going to be different. I don't know which specific model, right? If you remember when we went into all of our data, no, all of our data, all of our notebooks, you can see we have a bunch of different notebooks. I don't know which one specifically has the model that was used here. That's something that Will, who left a little while ago, or Peter might know which specific one it used. But there's a couple of different ones you can look through. It's either DesNet or ResNet. I don't know remember which one. Okay. Yeah. So that's the one. Yeah. 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 Oh. Oh, okay. Yeah, and this one, it gets like, what was it, 96% accuracy, right? If you run this whole notebook, I think you got something like 90%, 96% accuracy. Oh, yeah. Oh, yeah. Yeah. But yeah, but if you go this one, right? If you play this game, right? Which is essentially you're trying to beat the model, right? Can you guess better, right? Whether it's benign or malignant? I'm gonna guess here benign. Ah, I was right, but the computer was actually wrong in this case. Right? You can essentially see, if I were to click a bunch of times, I'm literally just guessing malignant every single time. All right, I'm ending with an accuracy of like 60%, and this model is like 95% accurate. So you can see if you take the time, you mess with different hyperparameters, different structure for this notebook and such, you can get really high accuracy. And here, for example, in this example, not only did it guess it right, but it was 99.99% certain that this was the correct image. And yeah, that's essentially it. Here, the notebook just finished running, actually, yeah. So here you can see, you know, it's training, right? Again, this was only through the 2 epochs. Even though I changed it to 5, I didn't rerun it yet. But as you can see, it started out with around 55 for the training validation, and it jumps up. Actually, on our training, it ends up being between 65 and 70, but our validation ends up being like something like 80%. And then our loss, right? How off is it when it guesses? That also went down, which is what you want, right? You want your accuracy to go up and your loss to go down as much as possible. Any questions? Yeah, okay, so here and here. So essentially, right, the loss is essentially trying to calculate how wrong were we, right? And so if you kind of try to think through it, it makes sense why you start at high value and you end up lows, because at the beginning you're gonna be wrong a lot, right? Because you don't know. But as you go through, you're gonna be wrong less, so your loss value is gonna go lower and lower, and you ideally want to get as close as possible to 0, which would essentially be it's perfectly right all the time. Does that kind of explain it, or? Oh, so in this, the it works a lot better for like some other data where it makes a lot of sense. But think of this as that whatever guess it made, it could have been just really off, right? It works better on like mean squared data, mean squared error. Sorry, or you might like, let's say I was trying to approach to a number that was 3 and I guessed 5. Well, I'm off by like 2, right? That's kind of what's going on here. And here it just has to do, the reason why it's that number is because it has to do with the way that the equation works. I don't have the equation, I can Google it right now. Binary cross entropy Keras. And I think it might give me the equation, but it will run through that equation. That's what it would actually show you. Let's see. Does it actually give me the equation here? It does not give me the equation, but whatever the equation is, maybe. Yeah, there you go. It's this. So, well, maybe not this one, but it's gonna be some weird equation. Yeah. 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 And that's why for this one, right, I'm kind of focusing more on the accuracy, because the accuracy is, at the end of the day, we want to just categorize something, so we care, in this instance, at least for showcasing this, we care a lot more about the accuracy. Yeah. That involves, that kind of boils down a lot about Keras. You're not really supposed to understand like a lot of the lower level stuff to kind of get all this output, right? As long as you understand the stuff at a high level, you can get pretty far with it. And I guess, yeah, I guess we can, and then you continue with the game. I'll paste the specific link to the game in case you can't find it on GitHub. That'll be a little thank you for attending. There we go. But yeah, if you want to play this out by yourself, see if you can actually beat it. I predict that you will not. You will get crushed, absolutely destroyed by this computer. You might rethink your life decisions. You know, why I've been wasting my time with computer science. I've obviously should have just become a pre-med gang. But you know, don't worry about it. That's why we make the computers, because they can do this stuff better than us. All right. Any other? Actually, I'm gonna stop the recording here. Hopefully I was recording this whole time.